Those were the days. You will not forget.
Yeah, I already say that.
Right. So, for your entertainment and amusement today, we have a couple of things. We'll go over some problems. I want to do a little promised lecture on Lagrange multipliers. And I'll assign the problems for next week, which we have not gotten around to putting on the web yet. I'm falling behind on keeping the web up to date. I apologize.
That's all right, I'm an online teacher and I got the same problem.
What kind of online teaching are you doing?
Teach physics and math at an online high school.
Oh, yeah? Online high school.
Yeah.
Yeah, I'm putting a lot of faith into you in these problem set no papers.
Okay, so,
Yeah.
Wednesday, Friday, Wednesday, Friday.
Oh, 2 weeks worth.
This is the 16th, 18th, 20th, 23rd, 25th,
Really?
27th. And
I'll take whatever. Give me a Sharpie. Quill. Whatever you got.
so for Monday, no problem assignment except to read chapter 3.
Yay.
What does it say about
So then we'll start in with, where are we here? 2 and 9, we'll basically do 2 a day. 12 and 17, 19 and 23, 25 and 28, 32 and 35. So it's a bunch of them. 28, 29. Wait. Got something wrong. 25th. Oh, Wednesday the 25th.
Oh, Wednesday.
But you want 28, 29.
Yeah, 32 and 35, 19 and 23, 12 and 17, 2 and 9. Okay. This chapter is back to real nitty-gritty mechanics. It's chapter 3, and it's a long one, and it's got subjects that are often in other texts in 2 chapters, so it's quite a bit of material. So we'll take a good 2 weeks on it. And these are, for those of you interested in the qualifying exam, this next chapter is the one that's more likely to have problems that'll be on the qualifying exam.
There we go. Professor Knapp?
Not going to be too many horrible Lagrange multiplier problems on the qualifying exam.
Could I ask a quick question?
Yeah.
So my job at home is I do a lot of dishes, and I get home, I do dishes, and I put on my iPad on the windowsill, and I watch TV or whatever. But I've been kind of watching a lot of like this guy named Leonard Susskind. He's the
Lenny, yeah.
the physics professor at Stanford.
Yeah.
We're watching his classical mechanics, and I'm wondering if you.
Oh, really? I have not seen it, no, but I'll bet it's good.
Well, yeah, I was wondering, do you have any recommendations? Because there's also this guy from Norway. I'm watching his stuff too. I'm just kind of wondering, because I'm trying to figure out whether or not these guys use Goldstein. I'd like to see if I can find somebody.
Well, they probably Lenny doesn't, I would guess. But he
probably wrote it, huh?
Lenny Susskind is well known. He was, by the way, Jason's thesis advisor.
Oh.
Jason Kumar. And he's one of the brightest theoreticians around. A bit rebellious kind of guy who does his own thing, and
Yeah, I like him.
is a bit, doesn't run with the pack so much, and has been the pusher of a theory that has been sort of on the outs with an alternative to Susie that Xerxes loves. So he's an interesting guy, very bright guy, personally, I'm not so sure about it.
So, do the dishes, watch Leonard Susskind, I'll be safe?
I think you probably learn a lot, yeah. I should take a look at his lectures, I'll probably learn something.
Alright.
Whether they're too abstract or not, I don't know. That might well be. I could well imagine that they're.
No,
they're
actually, he
beautiful.
hasn't started something crazy yet. I
Okay.
mean, but I've only watched the first 2 lectures, which are like an hour long, but.
Well, cool. So they're a YouTube thing.
Yeah, and he has like all of his classical mechanics, all of his quantum and particle physics and all that kind of stuff.
He's written a number of books too, both popular and technical. So he's a brilliant guy. Okay. So I wanted to go through, before we go back to finishing up on problems, I wanted to go through a little wrap about the Lagrange multipliers. They are kind of a, as I've said many times, they're kind of a mysterious thing, so let me just go through this. And I'm going to go through, how many of you actually went through in the book this example that of the ball rolling off the hemisphere?
Actually,
Did anybody work it through?
That was an
Or
example.
did you go, oh yeah, that looks reasonable?
No, that wasn't. That was an exercise.
Huh?
That was exercise in the book. It wasn't an
Yeah.
example.
Well, yeah, but it's
I was actually working on that right now.
ah,
I got stuck though.
yeah, I was gonna say, it's not so trivial, even though, okay, as you will see. So all of this gets started when we write, this is pretty much starting straight out of Goldstein, just to get us booted up. Through M, lambda sub alpha, F sub alpha, dt. And these F sub alphas are the equations of constraint. So they're something of the form F of R1, R2, etc. is equal to 0. Which is the thing that makes this all a little weird. So you do the variation, and you wind up then writing it as delta I is equal to the integral 1 to dt, and then the summation from I equal 1 through n. And there's some counting of degrees of freedom that needs to go on here. dt, dl, dq I dot minus dl, dl, dq. Sub I plus sigma alpha equal 1 through m, lambda sub alpha df alpha dqi delta qi curly bracket close is equal to 0. And note that the QIs need not be independent here, and some quite often are not, which is, right, so we've been talking about the difference when you go to the generalized coordinates from nice separable coordinates. So we have not just mv squared, but we may have mv x v y terms, things like that. So then you wind up rewriting that then is d dt of dl dqk dot minus dl dqk is equal to minus the summation of lambda alpha df Q dq sub k. And that we define as equal to big Q sub k, which is equal to some generalized force. Generalized And notice that the units of this need not be newtons, or it could be something kind of strange. But in general, it'll be a force. So that's where we're at. And we're starting with these equations, which is so bizarre that these things are zero. And so you see, this is what I was talking about. If you look at this part here, this is a gradient operation on these two functions. And so if you have these two functions, can I, what?
Yeah, the equal sign in the middle?
Equals 0 and then he split it?
No,
No,
there's an
I
equal
just
sign.
moved it to the other side.
Yeah.
We just
So,
define that stuff on the right as QK, right?
yeah. But looking at this piece here, this is a gradient of these two functions. So this thing is finding, this is what I was talking about last time. If I have some function like this, which is the L in this plane, then this piece here is finding the slope of this, right? And so if we define a vector that has the direction of downhill, and we have some other function over here, it's finding the slope of that, some other function, and so it will have, the gradient will have different pieces here. So we're looking for that place where these are actually tangent to each other. The slopes are the same. And so the slopes are the same, but they haven't got anything to do with each other. So there's no reason that lambda has to have any particular value. Lambda is just a stupid scalar constant that is being adjusted, but we're finding the point of tangency here. So it's this mathematical point that most of the application of the Lagrangian is used by lots of people for finding a particular solution. So that's a nice geometrical interpretation, which I didn't think of, found on the web. Anyway, now to the specific example, which is what I really wanted. Well, that was part of what I wanted to get to. So now let's go to that particular problem. This other stuff is all in the book there.
The hoop on a cylinder?
Huh?
Hoop on a cylinder?
No, not the hoop on the cylinder,
Oh.
but the one that is gone by very breezily in the text, which is this. Okay. So the idea of the problem is to find the point at which, by the centrifugal force exceeding the ability of gravity to pull this guy down onto the sphere, this guy leaves the sphere. Which, of course, you can solve. Any of you could have solved when you're freshman year in college by just writing down
Energy.
energy and the centrifugal force times cosine of the angle. But we'll do it the complicated way.
Oh.
Is it not sliding or a ball rolling?
It's a ball rolling. Uh,
So we're gonna have to take
In
it.
this case, it is, so there's another, wait a minute, what did he say here? I did it for the case, I did it for the case of sliding. Did he do rolling and put in the moment of inertia?
I feel like it's just a point particle.
I think it was just the sliding. Where do you go here? Yeah. Slides down without friction. Not rolling, it's sliding without friction. Rolling, then we're gonna have to introduce another, the moment of inertia of the sphere and the rotational energy of the sphere. So slipping. Slipping without friction. Okay, so in that case, we can write down L is equal to 1/2 m x dot squared plus y dot squared plus z dot squared minus the potential energy, which is mgz, where we're measuring z from 0 from here.
Is that supposed to be an L?
Yep.
That's, yeah, I'm gonna switch over to writing the curly L for the Lagrangian, which I like better. I don't know why. Okay, so the constraint force in these terms, the constraint is just that r squared is equal to x squared plus z squared is equal to a squared. So you can do it, and you can do it in rectangular coordinates if you like, but it's going to get more, a little more ugly. If you change into polar coordinates, then the motion in one of the dimensions, namely r, the motion will be in theta, and r being a constant. So it is almost guaranteed to simplify things. So we write x over z is equal to cosine theta, and then we rewrite everything. So here's the way this goes. We write down t is equal to 1/2 m r dot squared plus r theta dot squared. And the potential is mg r cosine theta, and the constraint equation f of r and theta is equal to r minus a, which is equal to 0. So this is the thing that's always a little obscure in these problems, is figuring out what this stupid function is to put in here, and which is 0.
Sorry, what is that second argument? It's R and A or R and G?
R and A.
Okay, thank you.
A, because this is just saying that R is equal to A, right? As long as it's on the sphere, and that's what we're going to solve for, is where that
Alright.
eventually, well, lambda, which is going to be the constraint of force, is 0. That's what we're going to solve for. So now we write down the Lagrange's equation with the Lagrange multiplier in it, and we write down dl dr is equal to minus d dt dl dr dot plus lambda df dr is equal to 0, and dl theta, what did I do? Minus d dt dl d theta dot plus lambda df d theta is equal to 0. So looking here, then df dr is just equal to 1, and df d theta is 0. So now we have the Lagrange equations in terms of the Lagrange multiplier.
Professor?
Yeah.
In the equation, you have a lambda sub alpha. Does that mean that those lambdas are different? Or the Lagrange multipliers are the same for both?
In this case, there's only one constraint equation. So
Right.
There's only one Lagrange multiplier.
If that other one didn't go to 0, would those have to be two different lambdas, or?
No, in this case, it would be the same lambda.
Okay.
So, let's see, where are we? So now we can rewrite this, carrying out the derivatives. We get what the hell did I write here? R theta squared. Oh. 2. I've written something wrong. The LDR. Oh. I mucked something up here. So this is the LDR. So that's just M. Damn it.
I know, I understand that the Lagrange multipliers are constants, so they could be positive or negative.
Yeah.
But like in the initial statement with the Euler-Lagrange formula, you have d dt partial L partial R dot minus partial R plus Lagrangian partial F partial R, like at the beginning of the lecture.
I think he's right.
Yeah, lambda.
Because you moved
Yeah,
over to the
yeah.
other
We
side.
moved it in the other side and the sign changes, but it can be either sign.
Yeah.
Yeah.
So how do you want to write it?
Yeah.
Okay, I can't read my own handwriting here. 2MR, that must be MR. But theta dot squared R. Okay, so I had R theta dot squared minus mg cosine theta minus m R double dot plus lambda equals 0, and mg R sine theta minus m R squared theta double dot minus 2 m R dot theta dot is equal to 0. So then if we apply R equal A, we know that R dot is equal to 0 and R double dot is surely equal to 0. So we can get rid of those terms. And then we wind up with M